if we have the same problem, exactly the same problem in this one. We have the same throttling valve, we have same inlet pressure and temperature, we have same outlet pressure, and ask you what is the exiting temperature. But this time I just changed one word. I told you this is not ideal gas, this is a real gas, and I need to use van der Waals equation of state in order to represent or in order to find any property I need for this gas. So if we repeat the whole steps we did in the previous example, so this is what we will find. Let's get back to the example we have. So we will start with the total derivative. Okay, the select x as temperature. This is the variable I need to have. I have given information about pressure. This is a still throttling valve, so I use h. So now I have dt by dB at constant h. I need to find it. I will use the triple product, so I have this one. This one, I will use the expansion rule, and I will end up with this equation here. So everything here will be the same. dH by dP at constant temperature, it will be molar volume plus temperature times this partial derivative. This one here I found because I have ideal gas. So I said I have PV equal RT, and this is the case I have here. So the only thing will be different between this example and the previous one, the way of calculating this partial derivative. Because this one is calculated from equation of state. The first example, we have ideal gas. We have ideal gas equation of state. Second example, we have van der Waals equation of state. So this will be the only change we have in this one. So if we write the equations here, so again from previous example, so let me quickly write the equations. We have dt is dt by dP at constant enthalpy dP. And itself dt by dP at constant enthalpy, this one, equals minus dH by dP at constant temperature divided by Cp. And this last partial derivative here, dH by dP at constant temperature so this one from the expansion rule equals V minus T dV by dt at constant pressure. So this is the equation. The first equation, we get it from the total derivative. The second partial derivative, we get it from the triple product. And then the last one we have from the triple product. So now the question, how we can find this one. Any partial derivative contains VTP. This is obtained from equation of state. So this is from equation of state. So in this example, we have van der Waals equation of state. And van der Waals equation of state, it says we have V equal RT over P plus B. So after we substitute, here we have the value of A is 0. So this is why we removed it from the equation, and we have only B, only parameter P appears in the equation. So in order to find this one, then we have dV by dt at constant pressure. So this one will be d by dt for the first term, or T over pressure plus d by dt of the second term, B. B is coefficient, is constant, so this term will be cancelled. Derivative of any constant is 0. Pressure is constant, temperature is constant, so this will be R over P, and again dt by dt, so this will be equal to R over P. Okay. So put the equation we have here. So now then we can say that dH by dP at constant temperature, this is V minus T dV by dt at constant pressure. Put all the data we have. This is from the ideal gas equation, from the van der Waals equation of a state, RT over P plus B minus T times R over P. So this will be equivalent to B. Then we have dt by dP at constant H, which is negative dH by dP at constant temperature divided by Cp, so this will be negative B over Cp. Okay, then substitute in dt equation, then dt itself, which is dt by dP at constant enthalpy dP, this will be negative B over Cp dP. Then we can integrate this equation. So let's write the last equation. So we have dt, this is minus B over Cp dP. So now we can integrate this equation. So we have the integration from the inlet temperature to the outlet temperature dt equal integration from the inlet pressure to the outlet pressure minus P over Cp dP. So the left side of the equation will be T2 minus T1, which is T2 minus 30 equal B is constant, Cp is constant, so this will be taken out of the integration, so this will be minus B over Cp times P2 minus P1. And for this one here, we have the value of B was given, and B is 1.5 times 10 to the power negative 4. Cp is constant, it's 7 over 2R, and R is 8.314 in the SI system. P2 minus P1, the pressure was, in this example, I think was in Pascal or megapascal. Let me get this one. It was megapascal, so we need to convert it to like Pascal here. So we need to convert it to Pascal. So we have the outlet pressure is 0.1, inlet pressure is 1, and then 10 to the power 6. and only then to the power 6 to convert megapascal to Pascal to make sure that everything we have in the SI system. So now we have all this equation, we have all the parameters in this equation, everything is like substituted. The only unknown is the outlet temperature. Then by substitution, you will see that the outlet temperature is 34.6 degrees Celsius. So just changing the way we are modeling the substance from ideal gas to van der Waals. In the first case as an ideal gas, the temperature difference was 0. So the inlet and outlet temperatures are the same. If we change the way we model the gas and we use van der Waals equation of a state, now we have temperature difference of 4.6. The inlet temperature is 30 and the outlet temperature is 34.6. Clear? Any questions? So this is how we are developing the thermodynamic models to find the properties we have. So again, this one, the steps are the same steps will be applied in every example. Okay, the thing is how much you are like familiar with these relations. Just try to select the correct properties that makes the solution like much easier for you.